Go ahead.
Yeah. Played a central role in the development of the widely used beam and RC code for modeling clinical accelerator and the EGS brachy code for calculating the dose distribution brachy. He was the driving force behind the TJ51 protocol for calibrating beams used for external beam radiotherapy. And he was lectured and organized summer school related to the clinical dosimetry and courses around the world for the use of the EGS and RC and the BM and RC code system. So Professor Rogers' work has been highly regarded in the field of the medical physics, and he has been recognized with the gold medals for lifetime achievement of both the AAPM in 2010 and the COMP in 2012. In today's webinar, Professor Rogers will shed light on the dose on radiotherapy and guide us to answer the question, should we report the dose to medium or dose to water in radiotherapy? He will provide valuable insights and the practical tips that we can all benefit from. We are incredibly fortunate to have Professor David Rogers join us today, and I am personally from him. So let's give us a warm virtual welcome to Professor Rogers. Professor Rogers, the floor is yours.
Okay, I will go ahead to share the screen. I think we've worked this out yesterday. We'll see. And I can see, let's see, oops, sorry, trying to figure out which screen is being shared. Okay, sorry, I have to, and I have to start the slideshow. And you're just, okay, so you should just be seeing the screen, not the presenter mode. So, okay, well, it's a pleasure to be here and to share with you this information about this issue. I should point out that when I first gave this talk, it was in a memorial session for Jack Cunningham, who many of you will have heard of from the Johns and Cunningham books, and so I started with that, and you'll see I mention his work several times in this presentation. So there are many misleading statements in the literature about the difference between the dose to the medium or the dose to the water. And this is just basically a discussion of some of the related issues. In a paper back in June of 2021 in the Green Journal, there was an excellent review article, which I would encourage people to look at. There was a report. It was to report the dose to medium in clinical trials where available. A consensus from the Global Harmonization Group to maximize consistency. And there'll be, the final slide is a list of all of the references that I give during this talk, so you don't have to worry about trying to copy them down quickly as we go. So what are the underlying problems? And the first one is that modern treatment planning systems calculate the dose to the medium by and large. But early dose calculating algorithms, for example, the equivalent tissue air ratio method, which was developed by Jack Cunningham, they actually calculated dose based on scaling data for water using electron densities. And I'll come back to that and discuss that a little bit more, show what that means. But there's also confusion in the literature about what dose the convolution superposition codes actually report. Again, I will talk more about that, but it has been said several times that they are reporting the dose to water, but in fact, as I'll show, they're meant to be reporting the dose to medium. Another reason that the life gets complicated is that reference dosimetry, for example, TRS 398, provides the dose to water in the the standard beam, so to speak, when you're calibrating your monitor units. And to further complicate things, well, not to complicate things, but ICRU 83, which was a report back in 2011, talking about IMRT radiotherapy mostly, they recommended reporting the dose to a small mass of water in bone using stopping power ratios. And I will talk more about what that means in considerable detail in the rest of this talk. But the thesis here is that when you're talking about the dose to bone, what you really care about is the dose to the blood and the blood cells interior to the bone, and they are more water-like. And again, we'll discuss that in more detail in the rest of the lecture. So back in 2002, there was a counterpoint debate in the journal Medical Physics, which was relevant to this. It was resolved that the dose to medium rather than dose to water should be used in Monte Carlo treatment planning. And Helen Liu was arguing for using the dose to the medium. And I write that in the rest of this talk as dose to M sub M, M comma M, which means the dose to the medium in the medium. And she had a variety of reasons for doing that. She said dose to medium is inherently what is calculated in Monte Carlo codes. And so it should be related to biological effects. And then there is a way to convert from the calculated dose to the medium to the dose to water in medium. And that introduces considerable uncertainty. And I will talk more about that in the rest of this talk. But there's the good news is that there's little difference in most tissues. So she argued that might as well calculate the dose to the medium. And basically the calibration of the monitor units is basically the same for each. So it's not much of an issue there. And lastly, and this we'll talk a bit about this later on, a CT, which is what you use to determine the density or the medium that you're looking at, is a voxel averaged value. And so especially at boundaries, it's not necessarily one medium or the other. And arguing to why you would want to use the dose to water, and again, as I will denote here, this is the dose to water in the medium, okay? And we're mostly interested in water in bone, is where it matters. And this was Paul Keel who was arguing this case. And he basically said clinical experience is based on the dose to water. And so this is a good reason for wanting to use the dose to water. And as I will show you, that's no longer the case clinically for the last 15 or more years. But in 2002, it was a reasonably accurate statement. Many dosimetry protocols are based on dose to water, as I mentioned before, TG51 or TRS-398. And the medium is not necessarily well defined, so it's easier to talk about dose to water. And again, I'll show you some complications there later. And he made the same argument as this ICRU report 83, and that is that the biologically important cells are water-like. So you want to get the dose to water. And if you go back and look at the AAPM's task group 105, which was about Monte Carlo treatment planning in medical physics, it summarized these same arguments because they still applied when that was written in 2007. So this slide is just meant to show that the main issues involve bone, okay? And that's because if you look at this curve here, you'll see that the for the soft tissues, this is we're looking at the attenuation coefficient, or the mass attenuation coefficient rather, for tissue to water. So in the region that's of interest in external beam radiotherapy, you see that this is mostly very close to 1, within 1%. So it's not a critical issue, except for bone. And here you see that for bone, we're getting up to a 7 or 8% kind of effect when this is going on. So this is the one comment about that. So I'm going to be showing a whole series of example calculations to try and tease out some of the effects here. And I chose this particular geometry because there had been a variety of other papers using the same geometry and discussing this particular issue. So what we have is a slab of cortical bone here at between 9 and 11 centimeters depth in a big water phantom, with irradiated by a 6 MV beam with about 100 centimeters squared. And we can calculate here the dose to the medium in medium. So it could be the dose to water here, or the dose to bone here. Or we can calculate, we can treat the whole thing as being water, with high density water in this region from 9 to 11 centimeters. And lastly, there's the possibility of calculating the dose to water in the bone medium, where you think of it as being small elements of water. And I'll discuss more of that as we go. But just to, oops, why is it not going forward here? Okay, so this is just showing a depth dose curve for with the bone there, or with just pure water. And the pure water case is the blue line. And when there's bone at 9 to 11 centimeters, you can see that there's a reduced number. And this is partially due to the reduced, we saw on the graph that the mass attenuation coefficient was lower. And so not surprisingly, the dose is lower here. And I'm going to just zoom in on this region here, but I just wanted to show you the overall effect as well. So here's a blown up version of it, and you can see the important thing to note here is that the dose to the bone is decreased, and just upstream of the bone, you can see that there's, due to backscatter, electron backscatter from the bone, there's an increased dose, and we're looking at a few percent kind of issue here, 3-4%. And down here, just before you get to the back of the bone, when you're calculating the dose in the bone, there's a lack of backscatter. And then you can see in this region down here that there's a bit of a slight buildup factor region rather, as after you've gotten out of the bone. So that's the standard, and these are just, of course, all Monte Carlo calculations that are presenting this. Okay, so there are various correction methods which are used, and I mentioned the equivalent tissue air ratio. This was something which Jack Cunningham developed back in the 70s, and it became a very widely used commercially in commercial treatment planning systems in the 70s, 80s, and 90s, for example. And in this particular algorithm, what they said was that the dose in a heterogeneous phantom at some depth Z was given by the dose that would be there if it was just a pure water, homogeneous water phantom at the same depth, and then corrected by tissue air ratios. In this case, the Z is the actual depth if it was pure water. This is the real area of the beam. Whereas A hat is the effective area of the beam where it's taking into account the density of the material. And this is Z prime is the equivalent water equivalent depth of the point you're interested in. And the only reason I put these equations up is just to make the point here that this is now, we're treating the bone as high density water. Okay, it basically is just saying that it's water. Now it does take into account, you know, the overall effect of the width of the beam, the effective width of the beam, and the effective depth as well. But it's basically, it is indeed calculating a dose to water. And so this is now just an example. Again, in a Monte Carlo calculation, we can do the equivalent thing of just saying, let's make the high density water where the bone was. And so we can do that in this region down through the middle here, shown by the black line. And you can see that as you go through it, the attenuation decreases the dose because it's more dense. And after you get out of the dense region, we're back in normal water. And after a slight amount of time, we are now giving the same dose back here as you got when you were calculating the dose to the medium. So because now you've taken into account the attenuation from this highly dense region where the bone is. So this is just making the point that if you were using the old in quotes old-fashioned treatment planning system, you were getting the dose to water, taking into account the density changes, basically. Okay, so then what about convolution superposition? Because for many years, this became the standard treatment planning system in many cases, and is still widely used because it can be very fast for optimization calculations. And in this case, we've got the beam coming in along this line here, and we're talking about the point of interaction where the beam interacts with the patient or the phantom. And we're talking about the dose location is defined by R in this notation that I am going to use. And what's interesting is that there are several papers in the literature which make the statement that convolution superposition is reporting dose to water. And that may be, I'm not an expert in what's actually in the clinical treatment planning systems, but I think it's probably people believe this because it's printed out or exported from the treatment planning system as if it was a dose to water. But in fact, as I will show you in just a few minutes, it's actually calculating the dose to the medium. And that comes if we look at this equation, and this is a complicated equation. If you're not used to it already, I'm not going to really try and teach it to you too much right now. But this basically what we're doing is we're saying the dose at this point R over here takes into account the number of interactions here through what this terma term. This is called the terma, and this is just a 1 over R squared reduction from the intensity at the point on the surface. And the important point here is that it's using the attenuation coefficient of the material at the point where the interaction is occurring, okay? And this is what convolution superposition is nominally doing, and it's also taking into account the realistic attenuation along the path length in the medium. And then you've got what you call an energy deposition kernel, which says if I've got this interaction occurring at a point, how much dose is being delivered at a distance R minus R prime away. and what you have to do then is, traditionally where these come from are Monte Carlo calculations, which have been very detailed, but they were done for water, okay? So you start off with this energy deposition kernel, which is in water, and you have to scale it to take into account the realistic density that's being experienced in the calculation. But the critical point here really is in where the terma comes in, and you see that the terma is taking into account the actual attenuation coefficient for the medium. So if it's bone, for example, you're seeing this 7% change in the actual terma because of that factor. So as was mentioned, I mean, Monte Carlo is what I can use the most efficiently and quickly. So I took a standard code, which is called dose-RZ NRC. So this basically calculates the dose in a cylindrical phantom, and uses eggs NRC to calculate this dose. And I basically hacked that Monte Carlo code, so changed it to actually it used the real geometry for this slab phantom that we were talking about until they got to the point of interaction. But then as soon as the computer code had decided, okay, I am going to interact in wherever, the water or the bone, wherever it was, then because it's a computer program, I just had it suddenly treat all of the media as being water with the local electron density that that medium had. So this was this was basically scaling the energy deposition kernel calculation, and this was getting the terma part of the calculation correctly, and is what we say here. And this is just a very simple hack of the code, and it only handles slab geometries. It's not meant to be a general purpose duplication of convolution superposition. So now if we look at this same graph that we've seen before, the important thing is I've added a new line, and it's this blue line that you see coming down here, and it's lying right on top of the calculated dose to medium, except just in this at the interface, it doesn't see this lack of backscatter, and up here it doesn't see the backscatter from the bone in this calculation, because we've turned everything to water the instant the interaction takes place. But the important point from my point of view is that this now lies right on top of the Monte Carlo calculation in the bone for the dose to medium. And then past that, it agrees with the dose calculated either for pure water with the different densities or not. So I think this makes the point for me anyway very clear that convolution superposition is actually calculating the dose to the medium. It's not calculating dose to water. And Anders Shanaho, one of the main developers of convolution superposition methods and computer programs, he made this point in a publication nearly 30 years ago now. But as I say, there are still various papers in the last 5 or 6 years where people have, or in the last 10 years certainly, that people have misstated that was actually the dose to water. Okay, so that's convolution superposition. So what's the summary so far? Well, as we saw in that figure, the dose to the medium is about 4% less than the dose in water with the scaled density. So it's not a huge effect, but it's significant. The convolution superposition dose is giving almost exactly the same as the dose to the medium calculated by a Monte Carlo, except just near the interfaces. And so the arguments in whether or not to use dose to water or dose to medium, which said that you wanted to match previous calculations or previous clinical results, is actually invalid unless you were talking about very old clinical data, clinical data based on equivalent tissue air ratios, for example. Okay, so and that also means the dose to the medium calculated with Monte Carlo calculations is generally in agreement with previous clinical data if it was based on convolution superposition.
مين في اللوبيا والهاي؟ تعشى اللوبيا والكباب؟
Sorry? Okay, I guess that's not to me. So then the next question is, what about water-like material in the bone being the sensitive component, okay? And this is what ICRU 83 was arguing about, reporting the dose to a small volume of water in bone. Now, there may be cases where the damage to the bone itself may be the limiting factor in certain situations. And in that case, clearly you want to report the dose just to the bone. But in many cases, the doctors tell me, and I'm not an MD, right? So I'll take their word for it, that the dose that is of interest is the water-like, what we call bone surface cells, or the red bone marrow inside our bones. That this is the critical radiation sensitive part of the bone. And this is where this ICRU 83 recommendation came from. But then the question is, how do we go about calculating that? And the answer is that cavity theory it solves that problem. And the next little section here, I'm aware that I've spent a lot of my life worrying about doing research on cavity theory and calculating stopping power ratios. So some of the detail here may be a little more than is necessary for general understanding. But nonetheless, if we look at Bragg-Gray cavity theory, and we have an electron spectrum in the bone, so we can calculate. If you think of this as being the equivalent of cavity theory for an ion chamber, then this is saying that the dose to the medium is equal to the dose to the water in the medium times this stopping power ratio of medium to water. So this is just the standard Bragg-Gray cavity theory that we use with ion chambers all the time. Now, in this case, in the case of ion chambers, we know the dose to the air in the water phantom, and what we're interested in is the dose to the medium. But in the case here, what we're interested in is we've calculated the dose to the medium, and we're interested in knowing what is the dose to the water in the medium. So we turn that equation on its head, and we end up with the dose to the medium, calculating the dose to water in the medium is equal to the dose in the medium divided by the stopping power ratio, in this case of medium to water. Now, another very helpful and useful aspect of this is that the dose to stopping power ratio of medium to water is almost identical to the inverse of the water to medium. So in fact, you can do the calculation using the dose to the medium from your Monte Carlo calculation, and then just multiply it by the stopping power ratio of water to medium. And back in 2000, Jeff Siebers et al. Calculated these values of W to M, the ratio of stopping power ratio water to medium. And the good news was that this stopping power ratio was virtually constant everywhere in the phantom, independent of whether it was water or realistic phantom. They had several examples. Now, as I say, I've spent a lot of time calculating stopping power ratios. And so my first question when I started looking at this is, everybody, we all, in standards labs especially, we use Spencer-Addicks cavity theory, not Bragg-Gray cavity theory. How different is it in that case? And similarly, what about electron beams? Will this calculation work for electron beams? So this is a rather busy graph, but if we look now here, I'm calculating the stopping power ratio of water to medium. This is the one we need. And if we take the Siebers et al. Number, they said that as a function of depth, it's flat, and you get this, and this Bragg-Gray calculation, it's this red line that we see here. But if I now do a more, in principle, more accurate Spencer-Addicks, and I do it with the ratio to cortical bone, you can see that it's just about 1% different. And the good news is that it is not varying at all either as a function of depth in this in a water phantom or a bone phantom for that matter. And I also did the calculations for a 12 MeV electron beam, and you can see that in this histogram, and you can see that there's about 1.3% variation as you change the depth, but it's not huge. So this approximation of using the stopping power ratio is fairly robust, is the bottom line in this sense. And this is for bone, where we see this is a 12% effect. If we now look at most other tissues and compare the Bragg-Gray to Spencer-Addicks on this scale, you can't see any difference. Okay, so again, there's no real problem, and it's constant, and it's about a 1% effect. So again, we don't worry about this issue in tissues. And again, pushing this simple thing, I've already said that we actually use the inverse of the stopping power ratio, which is normally calculated. So I went ahead and calculated in the blue line here, you can see I calculated the stopping power ratio of water to bone in a water phantom. And then in this case, I calculated the stopping power ratio of bone to water in a bone phantom. Okay, and the good news is, if you look at these two numbers, this number here is 1/0.8874, whereas here I got a value of 0.8872. So the good news is they really are simple inverses in this case. And again, I apologize for going into those details, but it's just the kind of thing I happen to have done a lot of in my career. So then the real question is, what is the dose to water-like material inside the bones? And using a stopping power ratio works well if you have charge particle equilibrium of secondaries in your phantom, or at least for secondaries below some cutoff delta when you're using Spencer-Addicks cavity theory. So now the question I had is, what happens if you vary Spencer-Addicks, the delta in the Spencer-Addicks? And again, this is me being obsessive about what looks like details, but if we change the cutoff, so in virtually every calculation that you see in say TRS 398, we use a cutoff for ion chambers of a delta of 10 keV, and so that corresponds here. But when you're talking about bones and water, what I've said is that a cutoff of 10 keV corresponds roughly to a 2.5 micron range for the electrons that you're talking about. And if you talk about 1 keV, it's 42 nanometers. Okay, so this, to put in context, a typical human cell is anywhere from say 10 to 100 microns. So, and if we go up to using larger and larger values of this cutoff here, you can see the stopping power ratio is actually changing by a few percent. I mean, the extreme of 3.4% isn't relevant. We're never talking about 42 nanometers, but this becomes close to what the range that the people would experience or expect. So again, this is being very pedantic about a specific point. And so now we've put stopping power ratios behind us. We just let us accept that we've got this up to a factor of 12, which is what was recommended by Siebers et al. And is in the literature in a lot of places. And in order to get the dose to the water in the medium, you multiply the dose to the medium here by this stopping power ratio, and you get this red line up here. And you can see this is substantially different. We're now talking about, I mean, this is 12% effect. This is clinically potentially very important. And so that's what's happening there. Where did this line come from? I've accidentally drawn a line. I don't know how to get rid of it. Okay. Oh, sorry. I got to go back. What am I doing here? Sorry.
I think it's from the annotation. There's a small pin on the left.
Okay, okay, I'm just going to leave that line there. I'm sorry. I don't see where to get rid of it.
I think it's okay.
Yeah, okay. Okay, sorry, I've lost where I was in my. Okay, so I'd shown you this graph, and we talked about this 12%. And okay, so what is the dose to the water-like material inside the bone? We're still asking that. And if we're using a stopping power ratio, it works well for thin slabs in principle. But Nick Reinhardt et al. Back in 2018 suggested actually using mass energy absorption coefficients instead. I'm not touching anything. Where did that come from? What I decided to do was I decided to actually do some calculations where I, instead of worrying about stopping power ratios or whatever, I did the calculations with thin slabs of water in the middle of my bone phantom, and calculated that as for different thicknesses of the bone. And oh gosh, okay. So here you can see the same red lines and blue and stuff as before, but I've got a series of individual calculations here for the dose to the water in these thin slabs. And you can see that if I use a very thin slab of water, then I'm getting something which corresponds to the stopping power ratio times the dose to the medium down here. But now I'm actually calculating the dose there. And then as I make it thicker and thicker, you can see that the actual dose to the water in the middle of the bone decreases. And so again, as I repeat, human cells are of the order of 10 to 100 microns, different ones, I'm told. But if I had a bigger and thicker slab of water, then by the time it's 5 millimeters, it's right down as if the whole slab was water, kind of thing. So that suggests that you might just be able to use this mu-en over rho ratio, which would comes in around here, and so this paper by Reinhardt et al. Said let's use these mu-en over rhos. The problem is what value for mu-en over rho should we use? In their paper, Nick and his colleagues said it should be 1.061. I did the calculation in phantom, because I can actually calculate the spectrum and get the mass energy absorption coefficient ratios of water to bone at that point. I got 1.017 in the actual case of I think I probably did that in the one, well, I was using the actual spectrum, I guess, in the bone. But if I did the calculation for the incident beam spectrum, the 6MV, before it was in the material at all, I got 1.053. And going back to Jack Cunningham again, he published a paper. He was the lead author on a paper back in 1986, in which the value was 1.026. So I'm not. It strikes me that the idea of using the mu n over rho ratios just doesn't work, in the sense that we don't know what value of mu n over rho we should be using, and there's big variations in those values just based on calculations. Okay, so where does that leave us? At this point, we can see that the dose to medium from either Monte Carlo or convolution superposition look very similar, except the interfaces. So that's the easiest thing to use. And if the concern is a small mass of water in bone, the stopping power ratio correction is not applicable for cell size regions which are larger, as I showed in that previous graph. And there's a very interesting paper, which I'll discuss in just a few minutes, from Blake Walters et al. Back in 2010, and they found that values that were corresponded to the stopping power ratio, and I'll show you that, as I say, in a moment. And this mu n over rho ratios, using that, it seems to be subject to uncertainty. And if you're going to use that, then for very large regions where it appears to be accurate for sure, then you might as well just calculate the dose to water by just varying the density everywhere. So that's easier in your Monte Carlo calculations or your convolution superposition. So just back once again to this question about what's biologically relevant in bones. And as I said earlier, it's really, in practice, only the bone surface cells that are really sensitive, as well as the red bone marrow cells in gaps around the bones. So what is the dose to these cells? And this is where the work by Walters et al. Comes in. They have a very interesting paper where they actually took some micro CT images of bones. So here is an example, and this is a 1.2 millimeter size voxel we're looking at. And you can see the kinds of resolution they were looking at. They used 68 voxels in each direction, 18 microns each, cubic voxels. And so you can see they had incredible detail in the bone that they were looking at. And so what they did was they calculated the bone surface cells were the layer that were the 10 microns nearest the actual bone here that we're looking at. So that they actually did this very detailed calculation to look at what the blood surface cells were the dose they were getting. And then they did a second calculation where they said, okay, instead, let's just pretend we just have a CT scan where we have the average material in this 1.2 millimeter cubic voxel. And they did the calculation just using a homogeneous set of voxels. And they could calculate the dose to the medium, this homogenized medium, or they could calculate the dose to water in that medium, and they could do it on the fly. It's the equivalent of using the stopping power ratio. So here's their results. We're looking here as the dose per incident history in the various cells, and this is the number of the relative fraction of the cells that get that dose. And you can see that it's quite spread out, but there's a significant peak here. In this case, just a little under 7 times 10 to the minus 17 gray per history. And this is for the radiosensitive red bone marrow cells or for the bone surface cells. So they were not very different. And this particular calculation was for the densest kind of bone material that you can run into in typical patients. And then they did this calculation for the homogenized model, where instead of having the detailed geometry, they just had 1.2 millimeter voxels of the average value material. And you can see here that, first of all, if they just calculated the dose to the medium as it stood, they got these, the pink here. But if they then calculated the dose to the water in the uniform voxels, they got this spike here. And then the question is, what happens if we compare these two? And indeed, the dose to water in medium lies right on top of the actual dose they calculated on the individual voxels. Okay, so this is a very convincing paper from my point of view, showing us that indeed the dose to the red blood cells or the bone surface cells is given by this dose to water in medium. The only issue here is, and this was this difference here between the dose to medium to medium and the dose to water in medium was only 7%. It's not the 12% that Siebers et al. and that many people have been using. So this is an important distinction. And they also made the point that this was for the densest trabecular bone volume fractions that they studied. And as the density got less, it was, I think, 55% here, and it could go down to 10%. Then the distinction between these becomes smaller and smaller. So instead of being 1.07 difference, it was 1.02 or something like that. Okay, so the conclusions I've more or less said is that the issue only arises in bony structures. And even there, the difference is only significant if it has the high trabecular bone volume fraction. And in this case, the dose to water in medium scored in a homogeneous voxel representing the right density of bony material is close to the actual dose to the sensitive volumes. So basically, they're saying use the dose to the medium calculation times the stopping power ratio. Because certainly clinically, you'll never be calculating this directly with all the detail that's necessary. And again, I just emphasize that they got a valid stopping power ratio of 1.07, not 1.12. Okay, so that's as I say, I find that a very interesting paper. But now a completely different issue is the following. When you're in a clinical situation, you've got a CT scan for your patient, and you've got a voxel which has been assigned a density of say 1.4. So that's this line here. Then your treatment planning system has to assign them. If you're going to calculate the dose to the medium, you have to determine which medium you want it to be. And the problem is that soft bone could be down here with this particular stopping power ratio, or if it was cortical bone, which is just another kind of bone, right, a denser bone, you see that the overall denser bone, but it's the overall density is the same. Then you see that there's nearly a 6% difference here. Okay, so again, clinically, this is a problem because your CT scan is just going to give you an overall density, and you have to make a selection. And you can see in this, I've picked, of course, a worst case. This was originally pointed out by the Siebers et al. Group. So it's a problem. And here I've just got a slide from Atomic News in Sweden, where he and his colleagues, a variety of colleagues, did a whole series of calculations for different treatment planning systems, and they put in 3 different slabs of bone material in their treatment planning systems. And I'm going to just zoom in on the next slide so you can, whoops. And you can see here these strange, well, not strange, sorry. You can see that the different treatment planning systems give you different doses as a function of depth. And so it's clear that the ones like this one here with the dashed, this is a dose to, is the Acuros dose to water and medium, where they've used this 1.12 stopping power ratio. And here's the same calculation, just doing the dose to the medium is the red line down here. And now you can see there's just a great deal of variation. So I guess the point is that one has to be very careful if the issue of the dose in the bone is clinically important in some situations, then you are going to be faced with getting that. And really strange things happen here when I move my thing, when I move my mouse. Sorry about that. Okay, so bottom line conclusions. I mean, first of all, not only have I probably confused you, but the answer is that there are no simple answers. The good news is that the dose to the medium, which is what is naturally calculated by Monte Carlo or by the Boltzmann transport solvers, and in principle by convolution superposition codes, is consistent with most clinical experience. So that's the good news. And a simplistic correction using stopping power ratios to get the dose to a small mass of water in bone is likely to lead to possibly big errors. Even though, you know, the concept of being concerned about the dose to the blood cells is something to be thought about. And then in this discussion, I have just totally ignored the much more difficult problems in brachytherapy. If you remember back to the very beginning, I showed you ratios of mass energy absorption coefficients, and I was making the point that they were very close to 1. You know, for tissues to water in the external beam region, you know, between 1 and 10 MV, say. But if you recall that they skyrocketed up and down for different regions in the body, different tissues. You know, when you went down to, you know, if you were down at 30 and 40 keV for brachytherapy sources. So there's still a real concern there about what's going on. But there's still enough problems just doing the calculations accurately in brachytherapy to take those, to worry about those details at this point is the next step, so to speak. Okay, and then the last slide is okay. The last slide is just a series of references that I have mentioned here, and I believe it's being recorded. So if anyone's interested, they'll be able to get those. So okay, so I think I've gone a little bit over time from my point of view. So sorry about that, but. Okay.
No, thank you. Thank you very much, Professor Rogers, for all the valuable information you provide us today. And now I think some of our people have some questions. So now we open the door for questions. If anyone have a question to Dr. Rogers about those calculations. Yes, Dr. Ala.
Yeah. Thank you, Dr. Deep, for this great talk. Dr. Roger, the use of radio sensitizer, such as gold nanoparticles, is an established approach in radiotherapy due to their ability to enhance radiation absorption and increase the dose delivered. The question is how are these radiosensitizer simulated in the planning system, and is Monte Carlo simulation qualified to handle this approach? Yeah, thank you.
Yeah, that's a very current question. Of course, in that case, we're not interested in the dose to the nanoparticles at all. But for example, just day before yesterday, one of our graduate students in our department, not my own, but another one of my colleagues' students, was giving a talk where she was describing a series of Monte Carlo calculations where they were calculating the dose to the nucleus of the cell versus the dose to the cytoplasm of the cell. And depending on how many nanoparticles there were, what density you had, and how they were distributed in the cell. And the take-home message that I got from this, because it was a complicated talk as well as the concept, was that it is just that. It's complicated. It indeed definitely enhances the dose, but whether it's enhancing the dose in the nucleus or the cytoplasm of the cells, and it depends very much just on where the nanoparticles have gone, and people are spending a lot of energy trying to develop techniques for depositing these nanoparticles in the optimum location, right? I mean, if you could ensure that the nanoparticles only went to tumor cells, that would certainly make things ideal, but it's not easily done, as far as I know. And again, it's not. I've never worked on the question of how to deliver nanoparticles, but I do know that there are people. You know, that would be a big advance if you had a way of ensuring those things went to the tumors as opposed to everywhere else.
Thank you.
Thank you very much.
Yeah.
Any more questions to Professor Rogers? I think there is no more questions. Thank you, Professor Rogers,
sorry,
again for.
Sorry, can I ask a question?
Yes, go ahead, please.
Yes, thank you very much. I want to ask you one question. By calibration factors, we converted the charge to the dose in waters or dose in mediums. And I want to ask you for Monte Carlo calculation, there is a CT2 EDA, CT2 electron density curve. So yes, we are correcting a dose by the first step. We are correcting the dose from the charge to the dose by calibration factors. And from the second step, we are correcting the dose to the medium by the calibration curve. That's a flow in radiotherapy.
I guess I'm not exactly following the point. I mean, I agree that the one step is if we've got an ion chamber and we're using that to calculate the dose in a water tank. But then the next once
Yes.
you've done that,
Yes, converting the dose to the different tissues like muscle, bone, air inside the treatment planning system by the calibration curve.
well, it isn't by a calibration curve. It's you use the calibration curve to determine what is the density and therefore the material, depending on what kind of what exactly your treatment planning system is doing. So in the old days, in quotes, if you were using equivalent tissue air ratio, you would only use that calibration curve to establish the electron density at each point.
Yes.
But now when you're doing Monte Carlo,
Yes.
you take that calibration curve, which tells you from the CT Hansfield number to you get an electron density. You then have to assign a medium to it, and there are different techniques for doing that. And you know, I've seen people, you know, doing research on exactly how to do that best. I haven't been involved with that particular research myself, but I do know that it's an issue that requires some sophistication to do it. And as that one graph, that one figure I showed where let's see if I can get it back. This one here, this was basically, you know, your material density is something you get from a calibration curve of CT scanner, but then you have to worry about exactly which material it should be. So okay.
Okay, thank you very much.
Thank you very much. Thank you.
Thank you very much. Any more questions? Okay, by that, I would like to thank you again, Professor Rogers, for being with us this evening and for sharing the valuable information you provide us.
Let me. Okay, Dr.
Dr.
Safa.
Mustafa, do you have a word?
Yeah.
Yes.
Yeah. Thank you very much, Dr. David. Thank you for your efforts. Really, this lecture was very important and contains accurate and important information. I think this lecture will be a part of a series of valuable and important lectures held by Iraqi Medical Physics Society. We hope that this meeting will be repeated in other scientific lectures. Thank you so much, Dr. David.
You're welcome. It's my pleasure.
Thank you, Dr. Safa.
Thank
Okay.
you, Professor Mustafa. Thank you very much.
Okay, good.
Thanks again.
Okay, thank you, and
Bye.
goodbye. Thank you.
Goodbye.